So the basic idea is that when you do a within pupil estimation, all the pupil characteristics are controlled for. Ability, average ability. That's a point I should emphasize, okay? The average ability of the students is controlled for. But if a student has high ability in math and different ability in science, which is not likely, but perhaps less ability in reading, that could be a source of a bias. So that's a left out factor that I do not control in this study, okay? But I'll show you an approach to look at that. But to do a pupil fixed effect, what do you need? You need at least 2 observations per student, okay? It's enough to combine math and science together to do a pupil fixed effect. But you can combine math and reading and science and reading. So you can do permutation of the pooling of the data that allow you to have a pupil fixed effect. You can get 3 different estimates: pooling math and science, pooling math and reading, pooling science and reading. Okay? And I think comparing those effects, you can get a sense whether there is a specific bias due to the ability of the students in a given subject. For example, if you get from science and reading the same effect as you get from math and reading, or for science and math together give you the same thing when you pull instead of each of them reading, you would probably be safe in assuming that you're not biased in terms of subject-specific ability. Okay? The nice thing is that you control for anything about the school. If it's a high-ability school in terms of the parents in general, the school principals, the quality of the teachers, the neighborhood effect, the peer effects in general in the school, all that is controlled when you do a pupil fixed effect. Okay? All that, as I said, at the price of assuming that the marginal productivity of an hour in science is the same as in English, is the same as in math. Okay? That should be kept in the background, and we should not forget that. So what do I do? Okay? Let's think simple. So I have a test score for student I in school J and in subject K. Okay? So there is variation across students in the school they are at and the subject that I'm looking at. There's a pupil fixed effect. This is the variable of interest, the treatment of interest, hours of instruction in school J and times K. Okay? So here's something I want to emphasize. How do I measure hours of instruction? Okay? One bias could be that the school is creating composition of classes by ability and determining the hours of instruction by ability of the class. So it could be that one class turned out to be a very bright class in terms of math. The school will give them more hours of instruction than in other class. I know that in my country it's impossible. You couldn't have variation within school, within a grade, in the amount of time they study different subjects. There's a national curriculum, and there is some margin of flexibility for the school, but the school cannot discriminate across classes within a grade. But there might be in PISA, I don't know the details of the 50+ countries in my sample that well to make this claim strong for everybody. Okay? So the way I measure hours of instruction is the average for the cohort, okay, for all the kids in a school, not in a class, in a school. So 15 years old could be in a school when they have different programs. There might be an advanced class, might be a class for weak students, there might be a class for bright students. I don't measure hours of instruction at the class level. That could be totally endogenous at this age of 15 years old in high school. I measure it at the school level. Okay? So in a way, it has the spirit of intention to treat. Because it could be that you, in a student in a bright class, are actually studying more science than this average. Okay? And someone is studying less. So it's an intention to treat. So you can think about it as an instrument for the actual hours. The average as an instrument for the actual hours. Okay? So this is how I measure H. This is the student background characteristic. This is SK subject dummies. Okay, so it's a dummy for each subject. If, for example, the test scores in English are always higher, in reading always higher than in math, that will be captured by this. And then there are some unobserved characteristics of the pupil and the school. Once we introduce the school fixed effect, it kills these two effects. Okay? You see here that I don't have JK, okay? J and K, which is specific ability of the students by subject. That I cannot do anything about, and this is kind of a threat to this identification. Okay? And UIJK is the remaining unobserved error term. It's a very simple model to estimate. Okay? You can estimate it first as an OLS without the student fixed effect. You can estimate it without the pupil characteristic, and you can estimate it with a full specification like this. Okay? So let's start with the results. Just want to see how much time I have. Okay? So math, science, and reading. Okay? I have the measure of hours is a continuous measure, the way the average for the school in that grade. Okay? From the PISA data, the teachers report how many hours the kids, the home class teacher, how many hours they're studying in each class, every subject. So I have the data directly reported from the teachers, so I can average it for the cohort. When you look at a simple correlation, you get an effect of about 21. Okay? That means that 1 hour of instruction will give you 21 more points, according to these estimates, in mathematics. That's the OLS. Okay? So if the standard deviation is about 100, that's a fifth of a standard deviation. You add country dummies, it goes up. You add individual characteristic, it goes down a bit. Okay? So that's the OLS estimate. And you see that they are positive and very large in science, and they're positive and a bit smaller in reading. Okay? That's the OLS. That's a naive set of estimates. Now we go to the one with the pupil fixed effect. So this is the OLS, 1958. It's should be here somewhere. So that's hours of instruction, the OLS one. When you add the pupil fixed effect, it drops to just below 6. So it's about 6 percentage point of a standard deviation of the test score distribution. But it is much higher when you look at the test score distribution within pupil, when the standard deviation is around 30, 35. So that's already something much larger, okay? About a fifth of a standard deviation. And it's highly, this is the standard error. It's clustered within the school. So it's very significant. And this is the sample size, almost 500,000 students. That's the OECD sample. That's about 25 countries with the 2006 data. You get a huge sample. That's when you pool math, science, and reading. Now I show you here an exercise when you put only math and science. You drop language, reading from the analysis. So the fixed effect of the students is based only on 2 observations, in math and in science. And you see that the OLS is a bit higher, and the student fixed effect estimate is a bit higher. Okay? So actually this is significantly different from that. If you take the confidence interval of this, it doesn't get into this one. Okay? This one is out of the range. Okay? But it's not dramatically different. It's the same ballpark. Okay? So we get a positive effect much lower than the OLS. Here it's about almost a fourth. Here it's about almost a fourth. The OLS is highly biased upward. The student fixed effect is much lower. Okay? So this is, and when you do reading in math or reading in science, you get something in between this and this. Okay, and I don't show it here, but I have it in the paper. Okay? So this suggests that the time a kid studying math would have a positive effect on the student's test scores relative to any other subject. Okay? Any other subject. As I said, the effect size is about 0.06, so 6 percentage point if you look at the distribution across students, but within students, it's about 0.15 of a standard deviation. That's already not small. Okay? So the effect of class size in the Tennessee experiment in the Angrist and Lavy paper, it's about 0.2 standard deviation. Okay? Here it's about 0.15 for an hour of instruction. Okay. So now I start a long trip, a long road of doing robustness check, exploiting the richness of the PISA data. Okay? So let's look at the effect of in a sample of private schools. Okay? The PISA sample has many, many private schools. In some countries, like in the Netherlands, in Belgium, 65–68% of the schools are private. What do I mean by private? They are part of a church, some religious schools, but they are publicly funded. Okay? In some other countries, the private schools are totally private. Okay? So you see that this is what I got before on the full sample. Okay? I skipped here the table. Maybe I'll get to the private one. So let's go to this one, where, no, right. So, oops. Okay, so this is for the whole sample. This is for schools where admission policy doesn't take into account the previous test scores of students. So there is no selection of students by the schools. Okay? Schools do not choose students into the school based on test scores. And here, schools choose students based on their ability. Okay? So the students do not choose the schools, it's the schools who choose the students. So this is a huge selection where schools admit only high ability students beyond a certain level of ability. And what do we see here? The effect of instruction time is really not different from what I get for the full sample. 6 and 6.2. So why is this result important? Suppose that there is a school that is very strong in math in general. It emphasizes math, it emphasizes science. So it chooses students that are highly able in math and science. It doesn't choose students who are highly able in English and reading or in the language of the country over students who are highly able in this math and science abilities. So if that's the case and the results that I presented to you are biased because of subject-specific ability, you see that these results do not support that potential bias. You get the same results. So this is a subsample of schools, that do not care about your previous ability. It could be like the charter schools that Josh presented to you last week, when schools choose students based on a lottery or admission. Everybody can go in. If there is oversubscription, there is a lottery. This is this type of schools. This one is the type of schools that Josh presented to you in terms of the exam schools in London and in Boston and New York, where schools choose students based on an exam and determine by that exam their ability. You see that in the PISA data, these types of schools in this sample yield exactly the same results. Okay? That's one robustness check which I think is important.